condenser, an evaporator, and an ejector. Then what would happen here is that we have the rest is going to be some tubes here. So vapor which is leaving the unit, part of it is going to be entrained here, m dot entrained vapor, and the rest m dot condenser will enter to the condenser. Here we have m dot motive steam, and what will be leaving here is basically a combination of both. And here we have m dot entrained vapor plus m dot motive steam, and here the entrained vapor is going to be extracted at this point, and it will mix with m dot condensate, and here will be m dot distillate leaving here. On the other hand, there is cooling water, and the cooling water enters into tubes of the condenser where it will be preheated, and after that it will be splitted. Part m dot cooling water will go to the sea, and the feed is going to enter to the unit here. So here we have m dot cooling water plus m dot feed. So this is, I mean, in a rough sketch, what happens in this system, and what will be thrown away here basically, or not thrown away, it will be returned back to the power plant. This is our m dot motive steam. There's something I did not draw so far, which is the rejected brine. Now, in this example, the information that are given, so here we have example. That it's basically the same information that we have in the example that we solved last time. And I'm using the same number, so that's basically for the sake of comparison. T cooling water is 25 degrees centigrade. Information related to the unit, the compression unit for the ejector is 2.5. The feed temperature is basically 70 centigrade. We are looking for a unit productivity. So m dot distillate is 1 kilogram per second. The feed salinity, XF, is 42,000 ppm, and the rejected brine salinity is 70,000 ppm. Specific heat for the seawater is 3.86 kilojoule per kilogram Kelvin or centigrade. Again, related to the ejector, the motive steam pressure is 750 kilopascal. The entrained vapor pressure is 37 kilopascal. You see here it's much less than the atmospheric pressure. And then efficiency of, or effectiveness of the condenser is 0.9. And what is needed is just to evaluate the performance of the unit. So this is basically the kind of input information that we are getting for this system, and we need to evaluate the performance. I'm just dividing it just to make it easy for me to Now, if we need to solve this problem, the first thing we are going to begin with, as usual, is going to be the mass balance, which means that the mass balance equations in the evaporator, m dot feed, this is the inlet flow in, is going to equal m dot distillate plus m dot brine. The second equation is going to be m dot feed into x feed is equal to m dot brine into x brine. Now we have two equations in how many unknowns?
Two unknown.
Two unknowns. M dot feed, we don't know it, and M dot brine, we don't know it. But we know the distillate is 1 kilogram per second. We know the feed salinity and the brine salinity. So from here we're going to obtain the value of M dot feed, and we're going to obtain the value of m dot brine, which is m dot feed minus 1. 1 is that productivity of the water, which is m dot d. Now, having known these, next step, what we need to do is to get into the analysis of the evaporator. For the evaporator, the energy balance is going to state that Q evaporator is equal to m dot motive steam plus m dot entrained vapor. This is the vapor which is coming in, and it's going to condense here, FGS. Actually, what you do is that you go for the thermodynamic tables or the ES to obtain the value of HGS, but HFGS. But you will see that we don't know the temperature of the steam. Yet the pressure is not given. Let me get to the right-hand side, which is m dot feed that is going to be heated from T feed to TB plus m dot distillate HFG of the vapor. Now, HFG of the vapor, this is easy to obtain because this is basically HFG at T vapor, which is basically TB minus boiling point elevation. Boiling point elevation, as I mentioned, you can either have it in the form of correlations that can be given to you, or you can obtain it from the ES, or maybe the value can be given to you if you are talking about a quiz or so. So that's something, it's a function which can be obtained from, for you now, as you are staying relaxed at home, you can go to the ES and get the boiling point elevation. Even for the homework, you can do that. For the exams, I have to provide you the value of boiling point elevation. Khalid?
Yes, Doctor, in the energy balance, why didn't you consider the brine, the mass
Here is it. M dot feed
feed?
is basically m dot distillate and m dot brine. So all the quantity has been heated to the TB.
Okay.
Fine. Now,
Doctor,
next thing to do is,
do you
again,
hear
look
me?
at this equation. We don't know the temperature Ts. We need it. Why do we need it? Because we need to determine HFGS. So Ts is the saturation temperature at the pressure Ps. Do we have the pressure PS? Yes, we should have it. I can see there's somebody. Abdul Karim, I cannot hear you. Maybe you need to unmute yourself.
Do you hear me now?
Yes, I can hear you now. Go ahead.
Oh, okay. Doctor, have you taken my attendance?
Um, Let me check, Abdul Karim. I think you are considered present.
Because in this week I found my exam times work and sometimes not.
No, I heard you when I took the attendance. I called
Ah,
you when I heard you.
okay. I'm sorry for
No, no
interruption.
problem.
Just a small question. We
Go
can
ahead.
find HFG at the vaporization by knowing TV and PEV, right?
By knowing TV,
And
this
P
is
and
the
PEV.
saturation temperature at TV. We are talking about this area here. Look at the figure. We are talking about here, the evaporation that occurs here. TEV has nothing to do with it here. So this is occurring at the vapor pressure.
Okay, but
Is the boiling pressure here, TB, saturation minus boiling point elevation.
I understand. But how can we find HFG by only knowing TV? We should have two
No,
properties.
this is, remember, this is saturation condition.
Okay.
This value, if you consider, for example, something like a TS diagram, that I need HFG at a certain temperature. If you go to the thermodynamic table, you'll find that you are given the value HF,
Ah,
HG, and the value of HFG will be given. Some thermodynamic books will not give it, so it will be the difference between HG and HF.
right, yes.
So you don't need more than that.
I'm sorry.
Okay, going back again here, that the TS will be known if we know the value of PS, and we have a value here so that can give me, or that I can use to obtain PS. Look at this, the compression ratio, in addition to the entrainment vapor pressure. Because the compression ratio definition is basically PS over P EV. CR is 2.5, PEV is 37 point some or 37 kilo Pascal. So from here, I can know the value of PS. Knowing PS, then I can get the value of TS. Knowing TS, I can get the value of HFGS. So now I have all this information here, except that these two quantities I don't know. M dot, how much is the motive steam flow rate and how much is the entrained vapor flow rate. And this is where I'm going to refer back to the equation of RA. It's given here as a correlation. This correlation is a function of the motive steam pressure, entrained vapor pressure, and delivery pressure. So from here, the value of RA can be calculated. So I know this value. How do I know that? From the correlation that I showed in the previous slide. And this correlation would always be given to you. So you can make use of the correlation to obtain the entrainment ratio. What's the entrainment ratio by definition? It is M dot motive divided by M dot entrained vapor. Now you have one equation where the only unknowns are M dot motive and M dot entrained vapor. You have another equation where the relation between M dot motive and M dot entrained vapor is known. So you are going to make use of these two equations to obtain the value of M dot motive steam and M dot entrained vapor value. Now I know how much is the motive steam flow rate and how much is the entrained vapor flow rate. Then area, then QE is area of the evaporator, U of the evaporator into TS minus TB. The overall heat transfer coefficient is either given to you as a value, as you remember in the previous example that we solved on the single effect evaporation, we have considered UE to be 2 or 2.5, I don't recall the number, but it's something like 2 kilowatt per meter square centigrade. So that's a value which is known. I have to tell you also that if you are going to look at the book that I'm going to post on the blackboard, which is the book of Dessouky and Touni, you'll find that he is given the overall heat transfer coefficient as a function of temperature. So this is another polynomial you can substitute in to calculate the overall heat transfer coefficient. An approximate value, but this value is accepted. So the overall heat transfer coefficient is also a known value once the temperature is known. And here all temperatures are known in this example. Now from here we can calculate area of the evaporator. Then we'll get to the condenser. Actually, before we get to the condenser, now we can calculate the value of PR, which is m dot distillate divided by m dot m. And we already calculated m dot m here. So this value can be calculated now. The condenser, what's the flow rate that gets to the condenser? It will be m dot C, which is basically m dot distillate or m dot vapor minus m dot entrained vapor. Q of the condenser is going to be m dot C HFGV. So we can get it right away because these values are known to us. This is equal to m dot feed, we know it, plus m dot cooling water. This is what we're going to determine into Cp given into T feed minus T cooling water. So from this equation, we can determine the value of m dot cooling water. And we can say that our delta T1 in the condenser is equal to TV minus T cooling water. Delta T2 in the condenser is TV minus T F. And from here, we can calculate the log mean temperature difference, which is delta T1 minus delta T2 over ln delta T1 over delta T2. Q is equal to the area of the condenser, overall heat transfer coefficient in the condenser into the log mean temperature difference in the condenser. UC is either given to you or again, a function of temperature can be utilized to calculate how much is the value of the overall heat transfer coefficient in the condenser. From here, we can calculate the area. Once we have done that, we have obtained all the elements needed for the analysis for this example. So we have already started by one measure parameter, one performance parameter, which is nothing more than the performance ratio. We have done that. And the other parameters that would be interested from this system and from any desalination system once we are doing the analysis too is basically, so PR, we calculated it as m dot distillate over m dot motive steam, and specific heat transfer area is area of the evaporator plus area of the condenser divided by m dot distillate. This is meter square per kilogram per second. And specific mass flow rate of the cooling water, this is mass flow rate of the cooling water needed to produce 1 kilogram per second of distillate, and this has no units, it's dimensionless like this, dimensionless. So what we see here are the three basic components that we need as a representative of the performance of a single effect evaporation or any desalination system, thermal desalination system in general. What's the PR? What's the specific heat transfer area? What is the specific flow rate of the cooling water? PR means how good we are utilizing the energy to produce water. SA is related to the capital cost of the plant. What would be the surface area needed for the tube bundle in the evaporator as well as in the condenser? And the cooling water flow rate, which is the ratio between m dot cooling water and m dot distillate, that will help us in sizing the right pump, and it will be needed to calculate the running cost of operating the pump as the system is operating. This is typically what you would do in an example of single effect evaporation with TVC. Any questions?
Doctor?
Yeah, go ahead.
I did not understand the part which you said QE is equal to m dot m plus m dot EV just in the left side.
Yes,
Below left
I'll
side.
show it to you again.
You
What,
equated with
which
below.
is this part basically? You are talking about, let me change. You are talking about this equation.
Yeah. How you, yeah,
Here.
all these terms.
What happens here? Look at the figure. What is entering here is basically m dot steam In our case, the steam which is coming here is a combination of two components, entrained vapor and motive steam that are mixed together here.
Exactly.
So this is going to condense inside the tubes and give off the latent heat.
Exactly.
The Q given in the evaporator is nothing but this quantity multiplied by HFG of steam.
Yes.
This is energy added by the steam. It enters as saturated vapor, it leaves as saturated liquid. So the difference between them is basically HFG.
Okay.
Is that clear?
Yeah, that's good. But how you equate it to MF times CP?
Yeah, I'm coming to you now. So it entered as saturated vapor and then it has lost its latent heat of condensation and leaving a saturated liquid. So this is what happens to the steam. Now let's look at the other side. What this energy is used to do? This energy is used to, we have, as the m dot feed enters in, it is sprayed on the outside surface of the tubes. So the feed here, which is coming at a temperature of 70, should be heated first to a temperature of 75. And this is what's going to occur here. The feed is going to be sensibly heated from T feed to TB. Okay?
Okay. Okay.
Then, when it is heated, basically you are spraying the feed on the outside surface of the tubes. So thin film is going to form here on the outside surface of the tube bundle. It will heat the feed from 70 to 75, yet part of the feed is going to evaporate as well by this amount of heat given, which is basically the m dot distillate into HFG.
Oh yeah.
So the steam
Right.
that is entering there is used first to sensibly heat the feed to saturation temperature and then evaporating part of it. The feed is 2.5 kilogram per second, for example, and 1 kilogram per second is going to be evaporated, and the rest, which is the majority, the 1.5 is going to be rejected down as brine because it will not evaporate.
Okay. Clear. Clear. Thank you.
Today, which is related to now I don't see it. Don't see this. Yes. Now I'm going to launch a polling for you.
Doctor, we lost your voice. We can't hear you. Doctor?
طلع الدكتور اتوقع.
دكتور طلع.
عنده connection issue. He's coming back.
Sorry again, I was disconnected somehow due to the net maybe or so. So there is a poll here that I would like to share with you, and I'm going to launch it now. And I'm talking about ejectors, where ejectors can be utilized. If you remember, what I talked about of the uses of the thermovapor compressor or the ejector, in what applications are they used? Are you able to see this in front of you?
Yes.
Hello?
Yes. Yes.
Okay, so now go ahead, please. Since today we were discussing the utilization of the thermovapor compressors, we talked about this. I can see only 2 of you have responded to, oh yeah, now the number is increasing. 4. 5. 7. 8. So now 2, 3, 9, 10. So 2 more, 11, 12. Okay. Now I can see that 6 of you have said that it is used in desalination systems. 1 said that it's as a venting system for non-condensable gases, and 1 said, or actually 5 have said all of the above. The correct answer is the last one, all of the above. Ejectors are used for desalination systems as thermovapor compressors. They are used in desalination systems also to get rid of the non-condensable gases, but maybe you don't have to use steam there. You can use air. It will create vacuum, and through the vacuum, you are going to take out the non-condensable gases. It is used in the refrigeration industry because you are creating vacuum, and once you are cooling down the vapor, then its temperature drops, and accordingly, you can get lower temperature this way. So the correct answer is all of the above. Now I would probably share with you in the last maybe 5 minutes or so of the class, I would share with you like an ES file that, sorry, I think I had the ES file opened somewhere. When we have so many files, it's not easy to identify exactly what is it that we're looking for. So let me try to launch the ES and see if it will respond. Whiteboard. Waiting, single effect evaporation. This is a presentation. Show all windows. Oh, yes. Now I think I got the rest of them. And here's the file. So what you see in front of you is the analysis of the ejector written in EES, and look at the left. These are the input values that we have. TB is 75, compression ratio is 2.5, cooling water temperature is 25, feed is 70 degrees centigrade, distillate is 1 kilogram per second, the feed salinity, the rejected brine salinity, CP of the water, motive steam pressure, operation, and you don't have to use this expression of TS. You can simply write here that TS is nothing but, let me do it here in front of you. I would just comment on this and use the TS, T underscore S, as the saturation temperature for the given pressure. So we're talking about thermodynamic properties, and here we are considering steam. So basically it should be T saturation. Where's the temperatures here? Yeah, T sat for a pressure which is, in our case, it's PS. So it is T sat corresponding to PS, and the way that PS is written is basically P underscore S. So simply, without using correlations or something, you can use the saturation temperature by that expression here. And the PS is going to be calculated from the compression ratio definition. And you can see it down here. For the ejector part, this is the definition of the entrainment ratio, m dot motive over m dot evaporator, entrained vapor. The PS is compression ratio into the PEV, and the RA, which is the entrainment ratio correlation that I've shown you, has been given here. And the two correction factors, pressure and temperature correction factors, are given here. Otherwise, it's the basic balance that we have written for the equation. And when we run the system, basically, this is what we get. Look at the performance ratio. The performance ratio that we calculated in our example last time was 0.95. Now, just adding the ejector has increased it by something like 50% improvement in the performance by just adding this small component. I have to tell you that the companies all over the world that are producing the ejectors are only maybe 3 or 4 companies, that's all. But they are monopolizing that industry so that they are the only ones creating or manufacturing the ejectors, and everyone needs the ejector, has to contact these companies for it. Now, this is the surface area. Specific surface area, you'll find it less compared to the previous system because the area in the condenser is less. And the same thing applies for the cooling water flow rate. It is less in this system compared to the previous one. So this is some sort of a numeric example, which is the one that we solved by hand. Here you can find it in the EES. So now we're approaching the end of the class. So that would be it for today. And you can leave now. I'll be again, as usual, staying for about 5 minutes or so if somebody